today's lecture, we'll talk about semantic segmentation, and we'll see like how this is different from the binary segmentation we studied or the image segmentation we studied. And both of these are like kind of correlated problems. And then we'll have the final lecture, lecture 16 on Thursday. That will be on instance segmentation. Okay, so all these problems are related. And I think both these lectures are not that heavy. So we will try to cover like different concepts and try to cover like the important concepts in both of these lectures so that you understand like the differences between these problems and also have a better understanding of how we can solve these problems. Okay, so let's talk about semantic segmentation. Now, before going to the solution, how this problem can be solved, let's try to understand what semantic segmentation is. So image segmentation, we saw the goal was given an image, we wanted to get an idea of like what different segments or what different regions we have in that image. Okay, and it could be like as simple as foreground versus background. For example, if we have some object in a scene and we want to separate like that object from the background, that would be like a very simple case. Now, semantic segmentation is kind of related because again, we are going to make like this pixel-wise prediction. For example, like these three images shown on the top row over here. Okay, if you look at this image, so in semantic segmentation, again, we are going to make prediction about each pixel on this image. And that was the case with binary segmentation and image segmentation as well. Now, the difference will be, in this case, we want to assign some kind of semantic meaning to each pixels. Okay, if you think about binary segmentation, there also, it was kind of semantic because we were saying that which pixel is foreground and which pixel is background. Okay, so it's not completely semantic, but there was some information tied there as well, right? So in this case, we will clearly say that, okay, each pixel is a grass because grass has a semantic meaning, right? And whether each pixel is a sheep or not. So that's like the commonality between segmentation and semantic segmentation. Now, if you try to differentiate this with like the image segmentation we studied, for example, the SLIC algorithm, right? So there, the goal was to get like different small segments from this image, where what might happen is you might get like different segments for the sheep. So each segment actually belongs to sheep. So it has some kind of tie to semantics, but then you can't say that, okay, this is your whole sheep. It will just part of it. Okay. So that's like one big difference between what we're trying to solve here and what we tried to solve earlier. Similarly, you can see like in the second image, you want to say that, okay, which pixel belongs to a car and which pixel belongs to a building or a road. Again, you might imagine that these are like simple scenes. For example, this image on the left, you can just say that, okay, the green grass is the background and whatever pixel you have of the sheep, that's a foreground. So you can basically solve this as a foreground, background, or binary segmentation problem as well. Okay. So, but in more complex scenarios, what will happen is instead of just having two different categories, we'll have multiple categories, right? For example, you have road, you have car, you might have like sky as well, you might have trees. So there will be multiple categories. And for each category, you will have to say that, okay, which category like each pixel belongs to. Similarly, here you can say that you have water, you have pixels for cow and for grass. All right. And more likely, like in a more realistic scenario, you will see like the image will be very, very complex and not just 3, 4, 5. You might have like hundreds of different categories just present in one different scene. And again, depending upon like what different categories you're interested in. So that's semantic segmentation. And of course, for deep learning, you know, not just deep learning, like any computer vision problem, you need like some kind of data set to work on. And for semantic segmentation, we have Pascal VOC and MS COCO. So these two popular data sets are mainly used. Okay, and there are other data sets as well, but those two are the most important one. So this is like one key part of like scene understanding. If you think about autonomous driving, then we discussed this earlier as well, that if you have a automatic driving car, then you have a, like, let's say a camera which is capturing what's happening in the surrounding or in the neighborhood. Then just saying that a car is present, a person is present, that's not enough. Then we talked about object detection, right? Which will say, okay, which particular, like you will give like the bounding box of each category, which will say, okay, this is a person, this is a car. Now, if you have like those objects which can move and which you can define using a bounding box, that's fine. But let's say you have a object which is not like, which cannot be fit like in a rectangular shape, right? So for example, this walkway. So if you have to draw a bounding box for this, it's going to be mostly covering the whole image, and that's not useful at all. So in that sense, therefore, the semantic segmentation will play a very important role. You can also carve out the boundaries of odd shaped objects. For example, this sidewalk, or for example, like the road over here, right? You need to find the road boundaries, and object detection is not going to solve that for you. And if you don't have the road boundaries, you don't know those lines, then it's, I mean, your car will not drive automatically, right? You don't know like where to drive. So that's why, so that's like just one simple application where semantics of segmentation is very useful. Okay. So there are many others, for example, medical diagnosis, where you have to get like the fine boundary of, for example, if you're doing tumor detections, you need to know like exactly where the tumor is present. And of course, like it could be your fun projects as well, where you're doing some kind of image editing. There as well, if you, let's say you want to carve out some of the objects that you don't want in your images, then you need those fine boundaries, right? And then you'll just remove those objects from your images. So a lot of different applications you can have in semantic segmentation. So assistive living, like this is another very important application area. For example, like if a person is not able to see like what's happening in the surrounding, right? In that case, if there is automatic system which can give like a very good idea of what's happening in the neighborhood, whether it's crowded, whether it's good to walk, and there is no, let's say, maybe potholes on the walkway. So all that is very, very useful, and you need semantic segmentation to solve that problem. Okay, again, the medical diagnostics, we talk about that. Again, image editing, it can be very useful here. All right, so the most important data set, as I said, the Pascal VOC data set we have, there are certain set of object categories, I think around 20 categories we have in this data set. And let's try to understand the distinction between semantic segmentation, object detection, and you can say like maybe instance segmentation, which is the topic like which you're going to cover in the next lecture. So given this image, if you have to solve object classification, and let's say you have object categories as chair and table. So object recognition will just say that, okay, chairs are present and table is present, right? Then object detection will also tell you, okay, this is a chair, this is a chair. So it will just mark bounding boxes for all the objects, all the chairs you have, and also the bounding box for this table. Now, semantic segmentation is, again, it's going to give you information about what exactly each pixel is. For example, if red color is for chairs and orange color is for tables, so you will expect like output like this, image shown on the right here. Okay, so all these pixels which are orange, they correspond to this this table over here, and all these pixels which are red, they corresponds to chair. Okay, and black pixels are just background pixels. We ignore those. Now, how this semantic segmentation is different from instance segmentation? In this case, we are saying that, let's say this pixel is chair and this pixel is chair, right? But we don't care about whether we have multiple chairs. For example, in this scene, if we have 4 different chairs, semantic segmentation, it has no role in saying that, okay, there are 4 different chairs, and it won't differentiate between pixel of, let's say, this chair and pixel of this chair. In contrast, if you have to do instance segmentation, then the term instance, it says that you are also interested in different instances. For example, in this case, you have 4 different instances for chair, right? You have 4 different chairs. So you would like to ID these chairs. Let's say this is blue chair, green chair, or brown and green chair, right? So that's just color, but you can use some other IDs as well. Now, in this case, we have to know that, okay, this pixel belongs to the first chair, and this pixel is actually chair, but it belongs to the second chair. Okay, so you also need to separate different instances. So that's the distinction between these 2 problems, semantic segmentation and instance segmentation. All right, so there are a lot of methods to solve this problem, and of course, we're not going to cover all of these. We will cover like a very simple deep learning approach, which is a convolutional approach. And this you will see like how this can be easily extended from what we have already covered. Like we have talked about classification, we have talked about autoencoders, and how all those concepts are going to be useful in solving the semantic segmentation problem. All right, so let's start. Let's start with some of the basics. So fully convolutional network, again, I think we covered this in one of the lectures where the idea was, instead of having fully connected layers at the end, we will just convert them to convolutional layers, and we know how to do that. And there are some benefits about that. So we have already covered those benefits. So one of the benefit is, if your resolution of the input image is changing, then you don't have to worry about changing your network. Whatever network you have, it will still work if your network is fully convolutional. As against to, if you have fully connected layers, if you change the resolution of your input image, then you're going to have problem and you won't be able to actually process that image using such a network. Okay, so that's just one flexibility you can have. Now, what we can do is, we can use like such fully convolutional networks to encode the images, okay? And these encodings, or you can say like features, kind of represent what objects or what kind of different parts of objects are present in the input image. So we'll have that information over here. And that's what we use for classification as well. Now, the goal is, instead of just doing classification, let's say if you have 21 different categories, so you were going to predict 21 different numbers, what you're going to do is you're going to extend this network and do like this pixel-wise prediction. Okay, so we'll try to utilize these features and try to upsample those features and try to say which category each pixel belongs to. And this might remind you of the autoencoders we were studying, where you have this encoder branch and then you have a decoder branch. And the decoder was trying to actually, in that case, it was just trying to decode the original input. But in this case, instead of decoding the original input, we are just trying to get this segmentation map. And in a way, the autoencoders you have developed, that can also be used to solve this problem. You just have to have a different loss function where you will say that, okay, which category each pixels belong to, instead of just constructing the original image. All right, so that's also a viable solution. I'm not saying it will work very well, but that's a solution. It will give you some kind of results. All right. And in a way, this architecture which you're going to discuss, like this is also in a way a kind of autoencoder, not exactly the same, but it falls in that category. Now, we have these features, let's say 4096. Now, one issue is, these are kind of flattened features. So we don't have any kind of spatial information restored here, right? So whatever information we have, whatever values we have, this corresponds to the whole image. As opposite to that, if you look at these features of the previous layers, there is some kind of spatial information preserved, right? So in a way, you can say that, let's look at this second layer, which is 256 different channels. And let's say this height is, I don't know, maybe 56 cross 56. So in a way, we can say that, okay, one chunk of this activation map actually belongs to this image portion, right? And similarly, like the top right will be corresponding to this region. So we have some kind of one-to-one correspondence. We know that, okay, these features are actually corresponding to this region. And that's why these features are actually very useful for predicting this kind of segmentation map. All right, so the simple solution could be, you can just pre-train your network for classification tasks. All right. And if you remember, this is exactly what we did for object detection. We just took like a classification network and we train it for classification. And then for object detection, we just added few heads on top of that, right? Exactly, we are going to do the same thing here as well. So we will do classification, but we'll make sure that we don't have any fully connected layers. We'll just convert all of those layers to fully convolutional layers. So that's one minor change. And then we are going to use skip layers. So this is a concept. I will briefly explain like what this means. So we'll try to use skip layers to improve this segmentation quality. So the idea is, we want to use these intermediate features as well to make this prediction. And the motivation is because these features actually preserve some kind of structural information from the input image. and they have some kind of spatial correspondence as well. So that's why they are very useful. And skip connections are something when you utilize these features in the decoder part of your autoencoder. Okay, so you can also think of these as like the skip connections or the residual blocks you have in your ResNet architecture, right? You just pass these features to future layers. Okay, so those are called skip connections. Now let's try to understand like the solution. So initially your classification will just predict, let's say if you have 1,000 different categories, it will predict 1,000 different numbers. And each number will say which object is present. For example, if this is a cat, this activation is going to be high. So the first change, as I said, we'll make it fully convolutional. So we don't have any fully connected layers here. Everything is convolutional, and we still have 1,000 different predictions. Now, what we do is we use these 1,000 different predictions to predict this kind of feature map. Okay, so this is some kind of heat map where we will say that, okay, which pixel belongs to which category. For example, if it's corresponding to heat map of a cat, then we know that a cat is present here. And of course, we'll have the ground truth for that because ground truth is required to train the model. Then you will predict this kind of heat map, and then you will try to predict like very highly active values here. And then you will try to match that against the ground truth, which means that all these values should be low, these values should be pretty high. So that could be a very simple change to your classification network. And now you're actually solving the semantic segmentation problem. So one issue will be, because this is kind of a compressed and no spatial information restored, so this quality is not going to be pretty good. Now, what we do to improve that, we use these skip connections. Okay, so this is your CNN or FCN network, and these are different layers. So after the final layer, let's say you make this prediction, the heat map for each category you have in your data set, right? So in this case, you'll have to perform some kind of upsampling, because this is, let's say, 2x2 or 4x4. This has to match with the original input image, right? So for example, you have to upsample by 32 times. All right. Then what you do, you take on those features again, and you upsample by 2 times, and then use features from the previous layer prior to this. Okay, so these are the features. And since these are now upsampled, so let's say this is 1x1. If you upsample by 2 times, it will become 2x2, right? And these features are already 2x2. Then you can just add these features, or you can concatenate these features. There are different ways to integrate these. And then again, you make this prediction, like what kind of segmentation heat map you will have. And in this case, since you have already upsampled 2 times, you only need to upsample 16 times. Okay, considering like the total compression was 32 times from input image to the output image. Okay, so and you can assume that if this is 1x1, your input image is 32x32. All right, so you make this prediction. Then again, you can have more skip connections from earlier layers. And again, you will upsample these features. Again, let's say you upsample twice. So this will become 4x4. And these features are already 4x4. You take these features, you can concat or you can add, both works perfectly fine. And then again, make predictions. In this case, it's just 8 times upsample. So in a way, you are making prediction for semantic segmentation, and you're making multiple predictions. So this is kind of a prediction at different scales, but all are actually trying to make the same prediction where cat is present and the segmentation boundary for that cat. So your network will look something like this. Okay, that's going to be the output, and you will have the segmentation ground truth for each image. And what you will do is, for each class category, you will predict one heat map. And from the ground truth, you can extract like the heat map for that particular category and compute the loss. For example, if you have 20 different classes, you can have 20 different heat maps like S channels, where each channel corresponds to one of the class category. Now, let's quickly look at like some of the visualizations for the results you can get from these kind of predictions. Since this is like a very crude prediction, we didn't have any kind of spatial information here, right, in pool 5. So this is the result which we have. And you can see that you don't have any fine boundaries at all, but you just have rough estimation of like, okay, this is a person and this is a cycle. Okay, this is a cycle, this is a person. But if you start using features from prior layers, which have like more spatial correspondence, then you can see your performance is actually improving. And if you move further, it keeps improving. Okay, basically, if you use like maybe this layer as well, it will improve further, but again, your computational cost is actually improving a lot. And this was the actual ground truth, which says that a green pixel is a cycle or bicycle, and the orange or this other color is for person. Okay, so this is the semantic segmentation ground truth, and these three predictions might come from these three different channels. Right. So few things here, like I think I introduced some of these we have already covered. So skip connection, that's a very important concept. You will see like if you have to make some kind of dense prediction task, whether in images or videos. So dense prediction is again like for each pixel, you have to say something what is happening there. So for those dense prediction tasks, these skip connections are very useful. All right. So the skip connections, the idea is you actually pass your features from different layers of your encoder to the decoder part. If you try to visualize this, this part is actually your decoder. And the only difference between this decoder and the decoder used for autoencoders is, in this case, you're trying to make multiple predictions. But you don't have to do that if you think about this. You can just ignore this one and ignore this one and just keep upsampling, right? And keep adding these features and just make prediction at the end. Then it will be more close to your traditional autoencoder. The only difference will be you will have these skip connections. Okay. So one thing which is important, how you are combining these features. As I said, you can add these features, which is also fine. You can just concatenate these features that will increase the number of channels you have in your decoder. So slightly it will have more computational cost. You might get slight better improvement as well in terms of performance. So those are two variants. And of course, there can be like many different ways to do fusion, but you don't have to like go through those. These two are, I think, sufficient, at least for some reasonable results. The other important thing is this upsampling step. And I remember we have discussed this already. Quickly, let's quickly go through this. There can be different ways you can upsample your features. And in your assignment, you might have seen, I think some of you used this bilinear interpolation. You can use trilinear interpolation as well. You can do repetition as well. So a lot of different ways there. And this is just one way to upsample, which is nearest neighbor. So let's say this is your feature map 2x2, and you have to upsample by twice. So let's say 2x. This is going to be 4x4. So you can just use nearest neighbor. You can just repeat this value 1. All right, you can just repeat this value 2, 3, and 4. And that's your 4x4 activation map. If you think about this, this is not even like close to max pooling, because max pooling is something you have different numbers, right? And you just pick the maximum one. But we do have a variant for max unpooling as well for upsampling. We will talk about that as well. But this is like slightly simpler than that. Another complex way you can do this is you can actually learn this upsampling. All right. And I'm not saying it will work pretty well or much better than this nearest neighbor, but that's just one variant. And we have seen like for some problems, it does work well. Some problems it doesn't. Okay, so it's hard to say. But let's see like what that variant is. Now, what you can do, if you have to upsample from 2x2 to 4x4, which means that each pixel is going to give you 4 different numbers, right? So what you can do is you can actually use 4 different kernels, right? And those kernels could be just 1x1 kernel, and you can apply on this. So the first kernel will give you this value. The second kernel will give you this value. Third kernel is going to this value. Fourth kernel is going to this value, right? So then those kernels are actually learnable. So in this case, you're not just doing nearest neighbor, you're actually learning how to do upsampling. And if it can be like same as nearest neighbor as well. Let's say the kernel you learn, it has just value of 1. Okay, it's a 1 cross 1 kernel, but what it's learning is just 1. Then it's equivalent to your nearest neighbor as well, because we'll just multiply 1 by 1. You're just going to get like these 4 numbers here, right? Same for 2, you'll just get 4 times 2. But again, that number is being learned, so that's just one variation. Okay, the other, I think this is more complex. I think this is something which you did for your assignment as well. Of course, you didn't write this code, it was already available. But in the background, this was happening. Okay, so depending upon which location you are going to perform this bilinear interpolation. Okay, for example, let's say you have 10 and 30. So those values will move like in the corners. Okay, 10, 20, 30, 40. So you have 10 here, you have 20 here, 30 and 40. That's fixed. Now, all the values in between, you are going to use interpolation to estimate those values. And equation for interpolation will look something like this. I understand this is complicated, but it's actually pretty simple. It's just trying to give some kind of weight to each of these 4 values, depending upon how far these values are from that location. It's that simple. So if you think about this, is just weighted average. Okay, and so this is 2-dimensional, but 1-dimensional version of this you have already done for, if you remember, like your histogram of gradient, right? The way you created those bins. So in those bins, each value goes to like multiple bins depending upon where it lies in your orientation circle, right? So that was weighted average, and that was considering the distance of that angle with the center of the bin. So that was again bilinear interpolation, but again in 2-dimensional. In this case, 1-dimensional. In this case, the same thing is being done, but it's in 2-dimensional. So if you think about this, like if you have to find the value of this location, then what you're going to do is you're going to find out how far this location is from 10, how far this location is from 20, how far this location is from 30, and how far this is from 40. So if 10 is very close, then it will utilize 10 a lot. So the weight for 10 will be pretty high. And again, what value you are going to use for 40, it will depend upon how far this is from this location. And these numbers are actually just computing that. If you look at this number here, right, it's just computing the distance. So y2 and these y's are the coordinates, the y coordinates, and these x's are the x coordinates. And these capital Q's are the 4 values. Okay, 1, 1, 2, 1, 1, 2, so 4 different values. So these numerator and denominator, they are just trying to compute how far the pixel location is from 4 different values. And the bottom is just the normalizing factor. Okay, so that's bilinear interpolation. Now, the other upsampling technique, which I was talking about, is max unpooling. And this is also very interesting. Okay, and this, I think, was the approach which was used for the first fully convolutional network when it was used for semantic segmentation. Now, if you remember max pooling, you have your activation, feature activations, right? And max pooling, you have some kind of window, which will decide like the size of the neighborhood. And then you have some kind of stride. And let's say we use a stride of 2 and we have a 2 cross 2 kernel, then you can see that clearly if you perform max pooling on this kind of feature map, you're going to get 5 from this because that's a max value, 6 from these 4, 7 from these 4, and 8 from these 4. So this is your max pool output, which is 2 cross 2. Now, this is the encoder part. We want to repeat the same thing on the decoder end. Okay, because if you think about this, what's happening here, if you're picking 5, at this point, we really don't know like from exactly what spatial location this 5 came from, because that information is lost, right? This is just 2 cross 2, but that information is present in this 4 cross 4 map. We know exactly the 5 was actually the bottom right corner of this box. Okay, and similarly, if you go to like the previous layer, you might have more fine-grained information. So the idea here is, how can we utilize this information when we are performing upsampling? Because right now, the previous approaches we saw, for example, when you were just doing nearest neighbor, you were just repeating 1 into 4 different values, right? Because you don't know like from where exactly this one came from. So what we can do is, when we are doing max pooling in the encoder, we can try to remember which element was actually getting picked. For example, if 5 was picked, just store this value, the location of this number 5. And when we are doing upsampling, we utilize that information. For example, if we have to upsample this 2x2 feature map, we know that, so 1 is corresponding to 5 here, right? Again, this is coming off like a lot of transformation, so don't worry about how 5 converted to 1. So let's say we have 1. Now we have to see, while unpooling, where will 1 go? We know that 5 came from this location, right? So we just copy that. We copy this 1 to the same location from where 5 came. And rest of the locations are 0. And which is fine, because anyways, these numbers were ignored, right? 3, 2, 1, they're not playing any role in like these feature computations. They were just ignored when we perform max pooling. So they might not be required for upsampling as well. So we just put 0 here. Okay, so that's the concept of max unpooling. And you will have like a long encoder, you will have a long decoder. Then the idea is you should have like corresponding layers. Like if you have some layer in your encoder, you should have a corresponding layer in the decoder as well, where you will try to match these indices of the max pooling elements, right? And of course, there are like a lot of other ways. As I said, you can learn these upsampling layers, and you can say like you can have deconvolution layer, and these 3 are just some variations how you can do. For example, if you have to go from 2x2 to 4x4, this is another interesting way. You can just perform 0 padding. Okay, and when you perform 0 padding, so this is your window size, and it's computing like, so stride is 1, window size is 3x3, and that kernel is just performing the transformation at each location, and that is going to give you 4x4. One thing is like for most of the values, 0 will be used, but still there is some learning being performed here. Similarly, you can have this kind of variation, and I think what's happening here is, this is a variant which we discussed earlier. For each location, you can actually have multiple kernels. Okay, and you can just place those values which are getting from multiple kernels at different locations of the upsampling output. Now, another variant of the center method here is you can actually insert stride into your activation maps, something like this. Okay, and then again perform the same operation. And then again you will get, in this case, let's say you're getting 5x5. Okay, so again, these are some variations how you can perform upsampling. And some of these have like their own advantages, which is fine. We don't have to go in that direction. Okay, so basically, as I said, you can use like a simple convolutional based autoencoder to perform semantic segmentation. And this is just one variation of that, where given an input image, you can have your the classification network, or you can say like the encoder convolutional network, where you can have convolution layers, max pooling layers, and at the end you have these flattened features, and then you can just repeat like all these operations in the reverse. Okay, and what you will need is like you will need some kind of uppooling or upsampling. And again, as we discussed, like there are a lot of ways you can perform this upsampling operation. You can actually use the indices of max pooling to do that. And again, these can be your simple convolution operations in between. So you have unpooling or upsampling, convolution operation, upsampling, convolution operation. And some variant of this, I think you already did in one of the assignment when you were implementing autoencoders. Now, like these are some sample results like from this kind of architecture. And here you can see that the resolution of the output actually will change a lot depending upon where you are actually predicting the segmentation map. And of course, you can just predict at the end, or you can predict like after each layer as well, right? So this is just showing that. And you can see like as you increase the resolution of your upsampling activation maps, the quality of result is going to be better and better. Okay, so these are kind of fragmented, but still you have some kind of structure, and you can say that this seems like a bicycle, but you don't have the fine boundary. because you don't have that high resolution here. So it will keep improving, and this looks pretty good, right? You can say this is a bicycle easily. Now, there are like several different ways to do this autoencoder kind of architecture for semantic segmentation. You can have simple encoder decoder, which we discussed earlier. This is more interesting. This is a very famous architecture called UNIT. And this is like very widely used in medical imaging field, because there you have like those images and you have to do segmentation of those let's say tumors, right? Or maybe different body parts. So it's actually very heavily used in that field, not there even like in computer vision community. So the difference between your this autoencoder based encoder decoder architecture and this unit is you have these skip connections. And now you know what skip connections are. Okay. And of course, there can be a lot of variations how we use these skip connections. Let's go through like exactly how this unit architecture does that. Okay, so before going there, so this is the basic convolutional encoder decoder based architecture. And in this case, what's happening, again, this is a traditional CNN architecture. And this is just like a reverse of that. And for upsampling, you can have the unpooling operation, like the very preserve like the pooling indices of your max pooling from the encoder. Okay, so that's one variation as we discussed. This is the second architecture we can have for semantic segmentation. This is a unit architecture. And if you look carefully, this is the input image over here, and all these blue arrows, these are the con operations. You can say con layers. So these are like two different con layers. Then your max pooling, the resolution is going down. Con layers, max operation, resolution going down. Okay. So this left half portion of this is encoder, and it's more or less same as this. Okay. Then you take these flattened features, and this is your decoder aspect. Now, as I said, there can be different ways. So in this one, we are just showing like you are using concatenation. Okay, so you're using features from the encoder half and just concatenating them with features in the decoder half. Okay, now one difference here is because these guys actually used odd-shaped images. I mean, we don't really need this, but the input size was pretty odd. And that was the reason, like when you have to follow these features to the decoder through skip connection, because there was a size mismatch, you have to take this crop. And this crop should actually match with the size of your decoder features. And then you can, if the size matches, you can just concatenate. Okay, so the size is 392 cross 392. But in this case, the size was 568, 568. So you can't take all of those, you just concatenate. Okay, so 64 channels will come and 64 channels coming from here, which makes it like 128. And then you can continue your convolution operations. So that was the only difference, like what like normally we do in a unit architecture, but what was done in the original work. And as I said, we don't need this crop. If it would be like pretty smart to actually use like a different resolution here, which makes sure that the resolution you have at this layer matches with the resolution at this layer, you can just take those features and concat. That's also possible. But they had to like take this crop like at every stage, which is fine. Okay, but you do understand like this architecture. It's the same architecture we have been discussing. This is the encoder, this is the decoder. So encoder, we have conv operations, max pooling, conv operations, max pooling, then flattened features. Decoder, we have upsampling, conv operation, upsampling, conv operation. We can just keep repeating that and create like deeper networks as well. And these arrows are just skip connections. You're copying features from encoder to the decoder. All right.